Thank you, Huacheng. So this is based on joint work with Moses Charikar, and in this work we look at an instance of the following question. There are n weights known between 0 and 1, W1, Wn, and also we have a constant epsilon that's greater than 0, and our goal is to get a 1 plus epsilon approximation to the average value of those weights, denoted by mu. So this is a simple problem, and we have two very simple algorithms as well. The first one is the trivial algorithm, where we just perform a linear scan and can be done in O of n time. And the next one, a little bit more sophisticated algorithm, is random sampling, where we simply take a random subset of the weights and output the empirical average of the sum in this random sample as an approximation to the true average. And the question is, how many samples do we need in this case? And it's not very hard to see that we need roughly 1 over mu samples, as long as mu is greater than 1 over n. And the reason we get this dependence is that there could be a very large weight item, let's say weight 1, and the rest of them could have weight mu. So unless we somehow sample that item, it's going to be we are not going to figure out what's the true value of the mean. And our work asks if we can do better in a more, if we have more structure. And the reason to do better is that we are gonna be able to sample heavyweight items with better probability. And in case it wasn't clear, here we don't know the numbers, and yeah. So this follows a recent line of work that obtains algorithms and lower bounds when the weights are structured and depend on a query vector. More specifically, we have a set of points given as vectors and a function that takes as input 2 arguments, one vector from our sets of points and a query vector, and that is how the weights are formed. So let me get to the specific setting that we study here. We have n vectors on the unit sphere in d dimensions and some log convex function of their inner product. We call that function phi. And the important quantity here that quantifies how difficult the estimation problem is the Lipschitz constant of the exponent, namely the function phi. So our goal and the topic that we study is to create a data structure by preprocessing these sets of points, so that we can very quickly estimate the average value of the sum of those weights defined by this function for any query that we might be given. So a few examples of what these type of functions include. The Gaussian kernel, or the log linear function, can be written as a linear function of this inner product on the unit sphere. The logistic function as well, and another example is some inverse polynomial kernel in the inner product. So basically, given a set of points and a log convex function phi, we want to preprocess the set so that we can very quickly estimate at any point on this sphere the value of this sum. And it's important to observe that by definition, this sum, the average value will be between 1, if we normalize with the maximum, and has minimum value of e to the minus twice the Lipschitz constant. And the number 2 here is like the diameter of the set on which f is defined, so it's 2, and times the Lipschitz constant. So it's a simple bound, but this is the smallest density that can appear with a given set of points and a function. So this problem is also known in different contexts as partition function estimation. Okay, and it has certain applications, namely in machine learning. In kernel density estimation, for example, we use the Gaussian kernel. If we want to define and sample from discrete distributions, namely those appearing in multi-label classification, where we might have 1,000 or 1,000,000 classes, and we want to assign some product, a person, to a certain label. Also, it appears if you want to sample from a language model defined through vector embeddings of words in NLP, and some other applications. The most important of which is, generally, if we are able to compute these sums quickly, we can have a fast evaluation of kernel methods. that is an important class of methods in machine learning. So this is the motivation. Now let me get to our result. So we show that given any constant delta greater than 0 and any convex function phi, where the Lipschitz constant is bounded but is slightly less than log n, then for any set on the unit sphere of n points, we can build a data structure that has query time at most exponential in the Lipschitz constant. And our restriction on the Lipschitz constant implies that this gives us a sublinear time, query time, to evaluate the sum or to approximate. And the preprocessing time of and space of the data structure is simply n times the worst case query time. And using this data structure, we can provide a constant factor approximation to the query, to any query with constant probability, and this can be by adding some epsilon squared factors, or log of 1 over the failure probability can be increased to have any no matter a very small failure probability. So in order to understand the basic restriction on the Lipschitz constant, if we assume instead of the points lying on the unit sphere, if they're in a sphere of radius r, a bound of the Lipschitz constant on the unit sphere implies a bound on the, for instance, for the case of the Gaussian kernel, of the maximum radius we can handle, and it basically it's 1/2 log n. So in order to understand this result, it's useful to compare it to random sampling that in the same setting of parameters would require the minimum of e to the twice the Lipschitz constant times n. And this factor here is the one that I showed you earlier. It corresponds to 1 over the minimum density that might appear. So in a certain sense, this type of algorithm gives a square root, like a square root improvement in certain over random sampling. But more importantly, besides the result itself, we have a single technique that gives a faster algorithm for a variety of problems, and kind of independently of what the convex function is. So that's, I think, what's the main point of this paper. To compare with previous work, as I said before, it improves on random sampling by, in some cases, by this much. It generally extends previous work in Fox 2017 that was had similar query times, but only for the Gaussian and exponential kernels, and a kernel with polynomial tails. And it's kind of incomparable to another work that treated only kernels with polynomial tails, whereas here we treat inherently functions that have exponential dependence in the inner product. And the key ideas are two. One is this idea that comes from this Fox paper of importance sampling through hashing, but this is not enough to handle this level of generality. So we borrow some ideas from harmonic analysis, namely partitions of unity and approximation theory, to kind of boost these techniques here to be more broadly applicable. And the other thing we do is we show that the restriction of order log n is actually necessary to get sublinear query evaluation under the strong exponential time hypothesis or the orthogonal vectors conjecture. And the details are not important, but even if we have n queries that we need to answer and only the average value of n queries, we cannot even do that for in subquadratic time if the Lipschitz constant is greater than some absolute constant times log n. And this uses a result by Rubinstein from Stock 2010 and a reduction to the approximate bichromatic closest pair. So the acetonic dependence on L is correct. The precise constant is not known, but this says that what we're doing is actually meaningful. And we provide the extension of this result to more general cases beyond the unit sphere, and instead of scalar functions to vector functions. And we also provide a connection to sampling from discrete distributions that was not known before. So in the rest of the time, I would like to give you an idea of the techniques that go into building these data structures. And starting from this Fox 2017 paper, And here, now the main idea to improve upon random sampling is to do some sort of bias sampling where we sample index I with probability Qi. And you can create unbiased estimators through this process. And if you want to minimize the variance, the ideal probability distribution to sample these indices is the one that's proportional to the weights. And then if you have such estimator, you can use the median of means procedure to get the probability of error down to the required level if you want. So what is the catch here? The catch is that the weights and thus the sampling distribution needs to depend on the query. And for different queries in this, in high dimensions, those distributions can have even disjoint support if the kernel varies fast enough. So the main challenge for this problem is to define efficient and query-dependent low variance importance sampling schemes. And the way we do that is we use this idea of a randomized space partition that is also known as locality sensitive hashing to sample these points in a query-dependent manner. So in Fox 2017, we showed that if we can construct a hash function where the collision probability, the probability that 2 points are mapped to the same part of this of the partition that induced by the hash function is proportional to the square root of the function that we wish to approximate, then we can define an estimator that has relatively small relative variance. In particular, if mu is the density that we want to approximate, we get relative variance, or equivalently sample complexity, 1 over root mu, instead of 1 over mu that random sampling had. And the estimator has a simple form. During pre-processing, we have populated these hash functions. And now, when the query comes, we look at this hash function and sample a random point from the hash bucket where the query maps to, and simply return the value of the function to be estimated divided by the probability that we sampled that point. Now, this property is referred to as the scale-free property of the hashing scheme. And this is the main bottleneck in applying this methodology to different estimation problems, because it's not always easy to find a single hash function that has this relationship with the function to be estimated. And in particular, in that paper, we were able to do it for a very limited set of functions using specific properties of the known locality sensitive hashing schemes. But in application machine learning optimization, we care more about inner products rather than the distance between 2 points that these exhibit. So our main contribution is to generalize the results on HBE and use more refined hashing schemes on the sphere instead of LSH, and then finally use approximation theory to show that whatever we do works well. So the first idea that we use is this idea of partitions of unity, and to motivate that, let's consider this one-dimensional setting where we have a function W0 between -1 and 1, and want to compute its integral over this range. So an idea is to partition the domain in small intervals such that the function is approximately constant within its interval. And instead of computing the integral of the sum, we're going to compute the sum of the integrals. And what we've gained now is that we have a much simpler, more localized function to integrate, and this is going to be easier. However, remember that now in our setting, this corresponds to, this value here corresponds to a certain inner product value between the points in the data set and our query. So it's not easy to construct such a partition in high dimensions. So we are going to need to have some soft version of the partition, but that means that there will be overlaps between these partitions. They're not going to be so smooth. And this, a set of functions that they sum to 1 at every point is called a partition of unity. And now if we can estimate its integral by rewriting it as a small number of integrals, then we can solve the original integral. So that gives us the basic plan. And the plan is to find appropriate hashing probabilities that induce sort of these soft partitions, then design an HB, and then also we decompose the function in a set of weight functions that we are going to decide appropriately, and then design a hashing-based estimator for each such function, and then bound the variance of the overall estimator. So, given a collection of a family of hashing schemes, each having a collision probability P indexed by T and some weight function WT that decomposes the function of interest, we can define this generalization of an HBE called the multi-resolution HB by, during preprocessing, we populate these hash tables sampled from this family, and now for each such hash table, we sample a random point from the bucket where the query maps to, and we return the HBE for each such weight function. Now, this might sound a little bit complicated, but we use a technique, a data technique that we had in this paper to bound the variance of this estimator, and we get the following two key design principles. The first one is that a good way to pick this partition of unity of how to decompose the function, given that you have a specific set of collision probabilities, is to write the function as to be proportional to the square root of the collision probability. So the partition of unity is defined through the sum of these functions that sum to 1. And if we analyze the variance of this overall estimator using these weights, it turns out that the variance is bounded by the variance of a single hashing-based estimator, where the collision probability is defined by the pointwise supremum of the collision probabilities. And thus, going back to the previous result, if we can construct efficiently a small number of hash functions such that their pointwise supremum approximates the square root of the function to be summed, then we will be done. Unfortunately, for low-convex functions, this square root operation preserves low convexity. And although we know I've talked about low convex functions, this overall scheme is general and doesn't have to do anything with low convex functions, as long as you can create an efficient hashing scheme that has this property. However, it's a non-trivial thing to achieve this. And how we do it, we use the so-called distance-sensitive hashing by O'Muller et al. In PODGE 2018 that basically gives us a non-monotone collision probabilities as a function of overall the linear product between the query and points in the data set. And this is how the effect of different parameters. The important thing is that these are kind of concave unimodal functions. So what we do, the bulk of our technical work is to construct this approximation. Basically, we show that there is a small family of hash functions indexed by these parameters such that the supremum of the log of the collision probabilities approximates the exponent, or half of the exponent. And we can control the error explicitly. And we do this by first approximating conservative function by piecewise linear functions, then using these basic elements to approximate any linear function by local, let's say, approximation. And then finally, bound the overall cost of evaluating these hash functions and the approximation error that affects the variance. So this is an example of the resulting approximations that we get. On the left is the approximation we get for the logistic function, and on the right of the square function. So to summarize, we give a single technique that gives us faster algorithms for a variety of problems. And the key ideas that we introduce are this notion of partition of unit and approximation theory that we borrow from harmonic analysis. And the intuition is that we kind of construct a stochastic version of the Riemann integral on the unit sphere. And we also provide certain extensions to other settings. And thank you.